Now let us find electric field due to uniformly charged sphere. So uniformly charged sphere. So consider a sphere of radius capital R. It is uniformly charged inside. Total it is completely like a nucleus. Inside total charges are there like that. Nucleus in an atom. It is totally charged sphere. Now our interest is to calculate the electric field at 3 points. One is outside, second inside, third on the surface. Right? This is our interest. For that, so here what we are taking, consider a sphere of radius r. Okay. See, let Q be the charge uniformly distributed over this sphere. Now let O be its center. In order to calculate the electric field outside the sphere, let us construct a Gaussian surface with radius small r. This is the dotted sphere over that original sphere. Now from Gauss law, we have electric flux phi is equal to Q by epsilon naught. Now electric flux can be written as integral of E dot ds is equal to Q by epsilon naught. See here at this point, let us take a small elemental surface area on the Gaussian surface. Let us say ds. And we know that electric field is radially outward in the same direction as that of ds. Now E dot ds is equal to simply EDS cos theta cos 0, that is equal to EDS, let us write EDS cos 0, that is equal to Q by epsilon naught. Clear? Now cos 0 value is 1. Is we want to find this constant value, let us take it out. Integral of ds is equal to Q by epsilon naught. Integral of ds value is the total surface area, that is just simply 4 pi r square. So E into 4 pi r square, here where small r is the radius of the Gaussian sphere, so is equal to Q by epsilon naught. Finally electric field E is equal to 1 by 4 pi epsilon naught into Q by r square, or put together we can write. So this is the electric field outside. It is like a point charge inside at the center O. So even if you put a point charge or a sphere inside a big one, then at a longer distance you will find the same electric field. Clear? Fine. Now let us find outside, that is inside electric field. Now let us calculate the electric field inside the sphere. Using Gauss law, we have phi is equal to Q by epsilon naught. Here let us construct a Gaussian surface inside with radius small r, inside the sphere capital R of radius capital R, and the Gaussian surface radius is small r. Then E dot ds for this sphere is equal to Q by epsilon naught, 1 by epsilon naught, and here charge is changing, you see. Total charge on the sphere is capital Q for the volume 4 by 3 pi r cube. Now there is a sphere of radius small r, it's a smaller sphere of volume this much, the charge will be proportionately decreases. So we take for this much volume the charge enclosed is only this much, that is total volume by this volume. So fine. Now E dot ds is equal to, as usual, this is the electric field outside, this is the surface area ds, and we get E ds, E integral of ds and theta between them will be 0, cos 0 is 1 is equal to, we get simply these two will get cancels, 1 by epsilon naught into q r cube by capital R cube. We know integral of ds for this sphere is equal to E into 4 pi r square is equal to 1 by epsilon naught into q r cube divided by capital R cube. See here, square and cube gets cancels, there we remains E is equal to q r divided by 4 pi epsilon naught into r cube remaining. This we get here. Clear? So this we can understand from here. See here, on the surface exactly, when you put small r is equal to capital R, either in this equation or in the previous equation, you will get simply it is q by r square. R and r gets cancelled, so r square. So these are the three cases we can observe. And if we draw a graph to the electric field and to the distance from the center, this is the r value. If it is capital R, it is proportional to small r increases, electric field increases up to capital R. Then after this, it is inversely decreasing, square of the inverse. So if it is the maximum value, electric field here we are giving, electric field, it is a small r value, it increases up to here, then decreases like this. So E proportional to R up to a maximum value to the surface when it is capital R, and after that E is inversely proportional to R square. This is how it is related.